Hello, and welcome to our video. I'm Alexis Huerta.
And I'm Kevin De Leon, and today we'll be discussing
rigid rotor.
So what is the rigid rotor? The rigid rotor is a quantum mechanical model system for rotating diatomic molecules. The model consists of 2 point masses, M1 and M2, which are at fixed distances R1 and R2, starting from the center of mass. The diatomic molecule vibrates as it rotates. However, since the vibrational amplitude is small in comparison with the bond length, we consider the bond length to be fixed. From what we have here, we could calculate the kinetic energy of the rigid rotor, which is equal to K is equal to 1/2 times M1 V1 squared plus M2 V2 squared omega squared. The values given within the parentheses is also known as the moment of inertia, which then can be denoted as I equals mu r squared, since the location of center of mass is given by M1 R1, which is equal to M2 R2, and we're given that R is equal to R1 plus R2. It's also important to state that mu is equal to the addition of atom 1, the mass of atom 1, times the mass of atom 2, divided by the addition of atom 1 plus atom 2. Now that we know the kinetic energy of the rigid rotor, we can calculate the Hamiltonian of the rigid rotor. As you know, the Hamiltonian consists of both the kinetic energy and the potential energy. Since the rigid rotor does not have any potential energy, then the Hamiltonian consists of only its kinetic energy operator, which is equal to negative h bar squared over 2 mu times the Laplacian operator. Since the system has a natural center of symmetry, we go from using Cartesian coordinates to spherical coordinates. So then our Laplacian operator is equal to this. Now that we have the Hamiltonian operator, then we could get the Schrödinger equation. Since the rotation of a linear rigid rotor is completely specified by two angles, theta and phi, then the wave functions depends only on them. So the rigid rotor wave function is denoted by y of sigma and phi. So we get that the Schrödinger equation is equal to this.
Rigid rotor seems small and maybe pointless, but it's actually a major component of microwave spectroscopy. Microwave spectroscopy's purpose is to look at the rotational aspect of the molecule. The transition between rotational states can be observed with a permanent electric dipole moment, which measures the overall polarity. Speaking about polarity, molecules in the microwave spectroscopy need to be polar in order to see any peaks. In the animation below, we can see the movement of electric dipole moment from positive to negative charge. On the right, we see a photo of a microwave spectroscopy. Some features are absorption cell, microwave radiation detector, and the radiation source. Fun fact, the radiation source is monochromatic, which makes it easier and faster to detect molecules than other spectroscopies. Now on the right, we see a simple microwave spectroscopy setup showing the major components, but not all. You can use these two concepts to find momentum of inertia, reduced mass, the energy, even the bond length. Let's do an example of what a possible question can be. The question here asks to calculate the bond length of H79Br based on rotational spectrum line spacing of 16.72. So the equation for bond length is I equals mu r squared. And the I is equal to inertia, the mu is equal to reduced mass, and r is the bond length. And so there are two things needed in order to find the bond length, and those are the inertia and reduced mass. The inertia is found by moving around the variables and finding the separation of lines in a rotational spectrum, which leads to this following equation. And H is equal to 6.626 times 10 to the negative 34 joules times seconds. And then C is the speed of light, which is 2.998 times 10 to the 10 centimeters per second. And this is equal to 16.72 centimeters. When we plug in our variables into this equation, we get our answer to be 3.35 times 10 to the negative 47 kilograms times meters squared. And this is our inertia. Now we have to find the reduced mass needed for the atomic mass for hydrogen and bromine. So hydrogen has a mass of 1.01 AMU, and bromine has a mass of 79 AMU. Our equation for reduced mass is mu, and then M1 times M2 over M1 plus M2. So we're going to make our H M2 and our BR M1. And when we plug in these numbers into our equation, we get 79 times 1.01 divided by 79 plus 101. And because this is an AMU and we want it to be in kilograms, we're going to multiply by 1.661 times 10 to the negative 27th kilograms divided by AMU. So our answer for reduced mass would be 1.657 times 10 to the negative 27 kilograms. Then going back to our equation to find bond length, we can plug in our new variables, inertia and reduced mass, and our answer will be 1.42 times 10 to the negative 10 meters for the bond length.